Okay, let's put this into practical application. Being able to graph it out is fine, but let's take a look at examples of how we would actually use this. So in the first case, it says write an inequality to represent all possible combinations of tile and stone that can be used to make a mosaic if tile costs $2.50 per feet squared and stone costs $6 per kilogram. And the budget for the mosaic is going to be $150. Include any restrictions on the variable. Well, first, I'm going to take the information that I have here. Tile costs this much, stone costs this much, and this is the total amount of money that I have. So I need to set up some variables. Let's just use X and Y. They're the standards that we like to use. I'm going to say that X is going to be the amount of tile in feet squared. I'm going to say that Y is going to be the amount of stone in kilograms. Now, if we're looking at a value question where it says that I only have up to $150, then that means that the amount of money I spent on one thing plus the amount of money I spent on the other one has to come in within $150. So I'm going to say, well, how much did I spend on my tile? I'm going to say that it's going to be $250 times the amount of tile I bought. How much did I spend on stone? 6 times the amount of stone I bought. And all of this has to come within $150. Well, I'm going to say that the total amount that I spend has to be either less than or equal to 150. I'm also going to state what are the restrictions on the variables. Well, I can't buy negative tiles and I can't buy negative stones. So I'm going to say that X has to be greater than or equal to 0, where it can be any real number, and Y has to be greater than or equal to 0, where it can be any real number. When I'm graphing the inequality, I'm going to isolate my Y. When I isolate my Y, I'm going to move everything over and say that I have Y has to be less than or equal to negative 2.5 over 6x plus 25. When I'm graphing in my calculator, I can go ahead, graph out y is equal to negative 2.5 over 6x plus 25, and I'll see that, oh, well, my window settings don't quite work again, so I'm going to have to adjust my window settings. So when I'm adjusting my window settings, I'm going to say that I have negative 5, positive 70, and the scale, I'll make 5 for x, and for y, negative 5, positive 30, and 5. Once again, I'm just changing it so that I can actually see where those x and y intercepts are. I'm going to draw in my axes. And then when I draw out my graph, what I'm going to do is I'm going to do a solid line. I'm going to shade in below that line, like what my graph is telling me, but I'm not going to extend it into the negative areas because I've already stated, well, I can't do that in my restrictions. So I'm just going to take these positive possibilities, and anything in here is going to work. And to make it a little bit clearer, I'm also going to state that, well, my intercepts here are going to be 0 and 25, and down here is going to be 60 and 0. Now I can pick any 3 ordered pairs or any 3 points that would fit inside of this graph that will work. So I can scroll through, I can look through all the points in my graph, and there's literally infinite possibilities. So I'm going to say, well, one case that I can see works is going to be if I have 5 and 20. If I go up 5 and up 20, it's going to come in around here. The next one I'm going to say is, well, what if I went up to 10 and 15? If I went up 10 and 15, it's going to come in somewhere around here. And if I'm going way more tile and a little less stone, then I'm going to say, well, what if I had 40 and 5? That's going to come in around here. All of these should work because they're all within my solution region. All right, let's move on to the second example. Sports equipment manufacturer makes footballs and soccer balls. One football requires 4 minutes on the cutting machine, while a soccer ball requires 3 minutes on the cutting machine. The maximum time on the cutting machine for both balls is going to be 30 minutes. Well, in this case, I'm not doing a value question, I'm doing a time question. So if I'm trying to solve for x and y, then I'm going to say, well, what am I making? In this case, I'm making footballs and I'm making soccer balls. So I'm going to say that x is going to be footballs cut, or number of footballs cut, and I'm going to say that y is going to be soccer balls cut. If I'm stating restrictions, I can't, once again, make negative footballs or negative soccer balls, and then beyond that, I can't make partial ones. It's not really going to count if I'm looking at how many of these things I'm going to produce. So I'm going to start by saying, well, x has to be greater than or equal to 0. And then beyond that, I'm also going to say that x has to be an element of the whole numbers because I'm not going to include partials. Same thing for y. Y has to be greater than or equal to 0, and y has to be an element of the whole numbers. The inequality is going to be, well, if it takes 4 minutes to make a football and 3 minutes to make a soccer ball, then I'm going to say I'm going to use up 4 minutes for every time I make a football, plus 3 minutes for every time I make a soccer ball. And if I only have a total of 30 minutes, the amount of time I spend on one plus the amount of time I spend on the other can only max out at 30 minutes. I'm going to isolate y, and I'm going to say that 3y has to be less than or equal to negative 4x plus 30, or y has to be less than or equal to negative 4 over 3x plus 10. I'm going to graph it out on my calculator, and then because it's going to be a rough sketch on here, I'm just going to state, well, where are my actual intercepts? In this case, my intercepts are going to be at 0 and 10, and at 7.5 and 0, and the solution region is going to fit with anything within this range. If I'm sketching a possible solution, I'm just going to pick a point that exists in there. Let's take a look in here, and I'm going to say, well, what if I had the point of 2 and 5? Looks to be within my solution region. So I'm going to substitute those in. There's my x value, there's my y value, and I'm going to substitute them into the original inequality that I created. So I'm going to say that I have 4 times 2 plus 3 times 5 has to be less than or equal to 30. 8 plus 15 has to be less than or equal to 30, and 23 has to be less than or equal to 30, which is true. So I know that this is going to work. Okay, let's take a look at one last example. So in this case, it says you want to earn at least, which means that I'm looking for a minimum or I'm looking for greater than this amount, at least $300 in total interest annually. You want to do this by investing some of your money in a bond that pays 0.4% per annum. Anytime I see 0.4%, I know that's the same as mathematically 0.04. And the rest that in a GIC that pays 5% per annum or 0.05 of the amount. Define your variables and determine an inequality that would represent the situation. Well, I'm going to say that in this case, X is going to be the dollars invested in the bond at 4%. Y is going to be the dollars invested in GIC at 5%. Restrictions on the variables, well, we've already seen this. X has to be greater than or equal to 0, and Y has to be greater than or equal to 0. We're not borrowing money so that we can invest it, because whatever we borrow is going to cost more. So my inequality, well, I'm going to state that 0.04x, or 4% of the amount invested in X, plus 0.05y, or 5% of the amount I invest in Y, has to be greater than or equal to 300. I'm going to isolate the Y again. 0.05y has to be greater than or equal to negative 0.04x plus 300. And then when I divide everything by 0.05, y has to be greater than or equal to, let's do this as a reduced fraction, negative 4 over 5x plus 6,000. All right, I can already tell when I'm graphing this out, if the y-intercept is going to be 6,000, I'm looking at big numbers. So I'm going to have to drastically change what my window settings are in my calculator in order to make this fit. Because I don't have to go into the negatives, then let's say if we were to do this, we could put it, however you want to do it. You could do it at 10,000, you could do it at, 7,000, 8,000, whatever it is going to be to actually be able to see what those intercepts are. When I draw out my graph, the big thing is going to be me stating what the values of these intercepts are. The first one we already know. That one is going to be at 0 and 6,000. The second one, or the x-intercept, is going to be at 7,500 and 0. In this case, because it's greater than, it's going to be anything bigger than that as long as everything fits into the positive ranges, going on forever and ever and ever. If I'm going to use a test point, I'm just going to pick any point that exists up in this positive region. In this case, I'm going to try the point that's right here. I'm going to check for 1,000 and 6,000. So I'm going to substitute that point in, and I'm going to say if I have 0.04 times 1,000 plus 0.05 times 6,000, is that in fact greater than or equal to 300? Well, this is going to give me 40 plus 300 is greater than or equal to 300, or 340 is greater than or equal to 300, which is true, and I know that everything works.